Okay, then we'll get started. Um, Again, thank you, Josh and Muskan, for all your support for the project and for your time today. So, yeah, this study examines how recycled water can be used in local council roadworks across NSW in a way that remains technically reliable, compliant with existing regulatory frameworks, and operationally practical for the councils. Rather than focusing on whether recycled water can be used in principle, our work concentrates on identifying when its use is appropriate in practice, where the real engineering operational risks arise, and what verification steps councils would need to make confident decisions. Uh, the motivation for this study began with growing water scarcity pressures across many regions of NSW, which are prompting greater consideration of alternative water sources in construction activities. Across both the literature and industry consultation, we observed that councils are increasingly encouraged to consider recycled water due to water scarcity and broader sustainability objectives. However, once recycled water enters the discussion, councils often face uncertainty, not only around engineering suitability, but also around cost behavior, logistics, and compliance expectations. These uncertainties can slow adoption, even where recycled water may be technically viable. This creates the need for a structured decision support framework that links engineering feasibility, regulatory requirements, and delivered cost considerations into one single practical pathway, enabling councils to adopt recycled water where it is justified while maintaining engineering performance and compliance. Yep. In response to this need, this project focused on applications where councils most frequently make operational water source decisions, particularly dust suppression and compaction, and evaluated them through both engineering and cost lenses. Our project was not to introduce new technical limits, but to translate existing specifications and guidance into clear decision triggers that councils can apply consistently across both metropolitan and regional contexts. The intended outcome is practical guidance that fits within current standards and procurement processes, allowing councils to make defensible site-specific decisions without needing to change existing specifications. Yep, to develop this framework, we followed a structured process. We began with a review of prior JFC work, regulatory guidance, Australian standards, and transport specifications to identify the engineering constraints that actually influence recycled water feasibility. We then developed a transparent delivered cost model that captures both water acquisition and the logistics factors before then applying the combined engineering cost framework to the representative metro and regional case scenarios. This all in all allowed us to test how decisions change depending on local conditions rather than relying on a single generic assumption. Building on our overall approach, we looked at how councils actually decide whether recycled water is an option for roadworks. One key finding is that recycled water isn't governed by a single rule. Instead, it sits across several frameworks that each deal with a different part of the decision. At a national level, AGWR provides a risk-based foundation focused on health and environmental protection. It's not road specific, but it does apply to construction activities like dust suppression and compaction. The NSW EPA and NSW Health then turned that into practical constraints around when recycled water can be used and how exposure is managed on site. In parallel, Austroads also provides the performance benchmarks that still apply irrespective of whether potable or recycled water is used. The key message for councils is that recycled water is not excluded by default. Rather, its use depends on demonstrating suitability through appropriate risk controls and technical verification. Yeah, and we'll now take you through the technical considerations of the project.
Yep, so once councils know recycled water can be an option, the next question is usually, what do we actually need to worry about? And the literature is surprisingly consistent on this. So from an engineering point of view, most of the sensitivity comes back to how water interacts with soil, especially during compaction. That's why salinity or EC is the main driver of engineering sensitivity, because it can affect moisture to density behavior and durability. So closely linked to that is SAR, which really becomes important in clay-rich soils due to dispersion and soak strength effects. On the other hand, things like turbidity and solids don't usually change pavement strength, but mainly affect operational reliability, like spray systems and downtime, rather than pavement strength. And then parameters like pH and specific ions are generally secondary, unless stabilization or concrete is involved. So rather than out, rather than asking councils to assess everything, the evidence supports focusing decision making on a small practical subset of parameters, especially salinity and SAR. When we translate the water quality evidence that we just went into actual roadworks, the level of risk really depends on the application. So for dust suppression, recycled water is generally a low structural risk. The water stays at the surface, so the focus is on exposure, runoff, and day-to-day operational reliability. Compaction is where the risk concentrates, so water chemistry can affect soil behavior and longer-term performance, even when density targets are met on the day. Concrete is different again because it's governed by AS 1379, so suitability is demonstrated through testing and compliance, not engineering judgment. But the key takeaway for councils is that short-term construction checks don't always tell the whole story. That's why the literature supports a risk-based approach, using verification where sensitivity is high, rather than assuming recycled water behaves the same as potable water. And that becomes especially important for stabilization, which is why the next section looks at stabilization as a special case. So while compaction is the most sensitive routine application, stabilization really sits in its own category, which is why we looked at it separately. It's already a tightly controlled process where performance is driven by moisture, mixing, curing, and quality assurance, with the water source just being one input. So the key question for this project wasn't whether recycled water changes stabilization, but whether it aids uncertainty beyond what engineers already manage. From the literature, that uncertainty mainly comes from chemistry, where salts can affect binder reactions, organics can slow early strength, and solids can influence mixing quality. That doesn't necessarily make recycled water unusable, though. It just means that it shouldn't be assumed equivalent to potable water without checks. So for stabilization, the real issue isn't compatibility, it's verification and confidence. A useful finding from this work is that New South Wales already has decision thresholds in place. So existing Transport for New South Wales specifications set limits for chlorides, sulfates, solids, and microbiological indicators for when recycled water is used. So we're not proposing new limits, we're simply showing how these existing limits can be used as clear screening points. This is especially important in regional areas where regular lab testing isn't always easy. That's why our framing of this suggests baseline testing per contact and per source. So enough to maintain confidence without necessarily overcomplicating any projects. This slide puts everything together into a simple decision pathway for councils. So first you identify the stabilization method and the relevant TF NSW specification because limits depend on the engineering context. Next, you confirm the water source and whether access and continuity are actually realistic on site. You then apply a basic threshold screen. In this case, if the limits can be met, the focus shifts to verification. So who's testing and how often? Where limits are met and verification and QA are strong, recycled water is conditionally acceptable. If limits can't be met or verified, recycled water becomes higher risk and is generally discouraged for councils to use. So the key point is that this pathway doesn't add new rules, it just organizes existing ones in a consistent way. Industry feedback supports this. So contractors indicated that potable water is usually used because it's easier to access and verify, not because recycled water fails. Where recycled water meets specification limits and stabilization controls are strong, there's no evidence of inherent incompatibility. So in practice, stabilization decisions come down to confidence in verification, traceability, and process control rather than concern about the recycled water itself. So once we understand where recycled water makes technical sense, the next question councils always ask is, what does it cost? I'll hand over to Sam, who will walk us through the cost model and how these technical decisions actually translate financially.
All right, thank you. So I'll be talking about the cost model structure. So this will be used in the coming sections, which will have case studies, which will go through the technical framework previously mentioned and the cost model structure, which I will talk about. The purpose is to compare delivered cost of different water sources through different conditions. The tanker volume from research is around 8 to 12 kiloliters. And with council contact, we are told to assumed as around 10 kiloliters per load as an average, unless specified otherwise. And the scope is that this is indicative planning model, not tender pricing or some kind of financial strategy. So in terms of the variables we will put in, we can go next. Yep. So the context will be between metro and regional council, where in our case, we are using the Fairfield and Tweed-Shire Council as comparison. The source is potable water versus recycled water in three conditions of wet, normal, and dry, and the tanker volume unit previously mentioned, 10 kiloliters unless specified. So the final delivered cost model will be the sum of water acquisition costs, travel costs, and in case operation impacts affect that transportation cost. So we also identified that transportation cost is the main cost driver. The water acquisition cost requires the price at fill point and tanker volume, unless specified. The tanker volume will be assumed as 10 kiloliters per load, as mentioned. The potable water is usually more easier to find for the cost itself directly, so this model may apply a bit better for like recycled water. And we go next. The transport cost is modeled on a time basis. So usually water carts are commonly hired on wet hire or hourly rates. And in this case, let's just define wet hire. Wet hire refers to hiring an equipment alongside an operator or driver, where usually fuel or other standard operating costs are considered within the hourly rate, but they may vary depending on the contractor. The total time cycle for one delivered load, where it is split into four sections as shown. So travel time is to go towards the destination and back. The queue time is waiting for any access if there's other tankers or people on site. The fill time is to fill the tank and connect, disconnect, and many other on-site operations. So we can go next. Yep. This is if the operation impacts have a noticeable impact towards the transport cost change. So we use lambda to represent the fraction of time lost to downtime, where near zero is considered negligible, and near one as a major impact, which high impacts will cause the increase in time and therefore the cost. The operational impacts can represent things like cleaning and testing when switching between recycled and potable use. Dual tankers require extra cleaning and may cause more delays compared to normal tankers. The access restrictions or extra procedures that slow turnaround, anything else that reduces effective productivity. You can think of lambda as a fraction of paid time you can't spend doing delivery costs, like a percentage. So go next. Yep. So in different conditions, these variables may be affected. So for example, increase the time, which leads to increasing in wet hire cost, or in, let's say, dry period, they may cause demand and restriction is causing delays, or some fill points may be considered unusable or unreachable. So they have to change to different operating sites, increasing distance or changing the queue time in that case. And any on-site operations that travel speed can vary with congestion, site access, or any operating rules or restrictions. There may also be more downtime or utilization costs, especially in dual-use tankers, and they may need extra cleaning and testing. So increasing time or damaging equipment will most likely increase costs overall. So, in summary, we compared delivered costs per 10 kiloliters load access across the scenario by changing the council context between metro and regional, in our case, Fairfield and Tweedshire, the water source between potable and recycled, and within three conditions of wet, normal, and dry. The delivered cost is split into three parts: water acquisition cost, transport cost, and if operation impacts does affect the overall transport cost. And the aim is to create a consistent structure that councils can populate with local values unless not specified, then you can have an assumption like the 10 kiloliters per load for a quick comparable cost check. And as mentioned before, is not a financial strategy or tender pricing. So I'll hand over this to the next person. The next section will focus on the metro and regional case studies. So Winnie will walk through the outline of the case study, which will use previous technical frameworks previously mentioned, and then the cost framework I just talked about. Yep.
Yes, so in the next slides, the cost framework will be applied into Fairfield and Tweedshire City Council as representatives for metro and regional councils. For each case study, the water source and quality will be assessed and the cost will be considered under different circumstances, including wet, normal, and dry. At the end of this section, a comparison will be introduced to highlight the impact of metro and regional unique characteristics on the water costs. First is the metro case study for the project, and we're focusing on Fairfield City Council. Fairfield is a good metro example because recycled water is already available through a major scheme, the Rose Hill Recycled Water Scheme, which supplies industrial customers across Fairfield, Cumberland, and Parramatta areas. In simple terms, Rose Hill Recycled Water Scheme starts with secondary treated wastewater from Sydney Water. That water is conveyed through the Liverpool to Ashfield pipeline to the Fairfield Advanced Water Treatment Plant, where it is upgraded to a higher quality using advanced treatment processes. After treatment, recycled water is stored on site and then pumped into the distribution system. The scheme then delivers recycled water to its main customers through a dedicated network. That network includes roughly 20 kilometers of pipeline supported by two pumping stations, Fairfield and Rose Hill, and two reservoirs, Woodville and Rose Hill. There are some requirements for the recycled water that are listed by the council including total dissolved solids less than 50 milligram per liter. The pH level range from 6.5 to 8.5, and etc. This requires the advanced treatment process to conduct the following methods: strainers, ultrafiltrations, reverse osmosis, and so on. For Fairfield, we estimated the delivered cost per 10 kiloliter load for both potable and recycled water under wet, normal, and dry conditions. The totals range from about 209 to 268 per load. The key message is that transport dominates the result. Transport is roughly 181 to 233 per load, while the water procurement component is only about 29 to 36 per load. So the truck wet hire time is doing most of the work in the total cost. You can also see the effect of the weather. In wet conditions, demand for dust suppression is lower and access to fuel points is generally easier. So we assume minimal queuing and the shortest cycle time, which gives the lowest delivered cost. As conditions get drier, demand increases, more users are likely to be filling at the same time. So we assume longer queuing delays at the fuel point. Those extra minutes increase the wet hire hours per trip, which directly raises the transport cost. And that is why the dry year transport cost is the highest. For potable water, the dry year case is higher again because the drought usage charge also increases the procurement component. Overall, if we want to reduce cost, the biggest lever is reducing cycle time, meaning shorter hold distances, faster filling, and fewer delays. Now I hand over to Monu for the regional case study and the comparison.
Okay, so building on the metropolitan case study at Fairfield, I will now move to the regional context and present the Tweedshire case study, which highlights how construction water costs and recycled water benefits change outside the metropolitan settings. So, Tweedshire Council manages its own potable water and wastewater system, sourced mainly from the Tweed River catchment with Clary Hall Dam, providing a drought resilience. Tweed produces recycled water from its local wastewater treatment plants, currently supplying to golf courses, sports fields, tree plantations, and various industrial precincts, demonstrating that fit-for-purpose reuse is already operational and reliable. Recycled water is treated to AGWR Class A using secondary filtration and chlorination. This delivers water quality that is fully suitable for dust suppression and earthworks compaction without the high cost of advanced metropolitan treatment like the reverse osmosis. For this case study and construction use, recycled water is supplied via the control tanker delivery from approved bulk filling stations with a typical haul distance of 20 kilometers. This chart breaks down the total construction water cost into water procurement, transport cost across potable and recycled scenarios. Across all scenarios, transport is the dominant cost component, accounting for approximately 78 to 84% of the total delivered cost. Water procurement costs differ between potable and recycled sources, but these differences are small compared to the transportation cost. In dry potable scenarios, additional allocation and scarcity related costs appears, increasing the total cost noticeably compared to the recycled water. The key takeaway is that while switching to recycled water, the water reduces cost, logistics efficiency, that is the haul distance, trip time, and wet hire, which has the largest influence on total construction water costs. This chart shows the cost advantage of recycled water over potable water across wet, normal, and dry years measured per 10 kiloliters. In wet and normal years, the recycled water delivers a consistent savings of about $19 per load, which corresponds to roughly 7.1% cost reduction. During the dry years, the saving increases significantly to around $32 per 10 kilo load, or about 10.6%, showing that drought conditions amplify the benefit of recycled water. The increase in savings during drought is driven by sharper price escalation in the potable water, while recycled water pricing remains comparatively stable. The main key takeaway is that the recycled water is always cheaper, but its greatest value is realized during drought when cost pressures and water scarcity are the highest. This table compares the construction water cost per 10 kiloliters between a metropolitan case study at Fairfield and a regional case study at Tweed. In normal conditions, the metro projects are cheaper overall, with potable water costing around $238 per load compared to around $267 in regional Tweed, reflecting longer haul distances and higher logistics costs in the regional areas. In Metro Fairfield, recycled water provides only marginal savings at around 1%, whereas in regional Tweed, the savings is much more significant at around 7% in the normal years. During drought conditions, potable water costs rise sharply in both locations, but recycled water remains more stable, increasing the saving to about 8% in metro areas and over 11% in the regional areas. So overall, the transport makes up the majority of total cost in both cases, around 75 to 84%, confirming that logistics, not water price alone, drive overall construction water economics. So now I will hand over to Aisha for discussing further project outcomes and implications.
Oh, yes. Stepping back, the project all in all delivers three key contributions for councils. First, an engineering feasibility framework that distinguishes between the lower sensitivity and the higher sensitivity applications, helping councils hopefully understand where recycled water can be adopted more readily and where additional verification is required. Second, a logistics-aware cost model that reflects how distance, access, operational conditions influence delivered cost, often more strongly than the water tariff itself. And third, a practical decision support pathway that integrates these technical and cost considerations, enabling councils to move from uncertainty toward defensible, evidence-based decisions. For IPWEA and councils, an important implication is that recycled water decisions do not have to be treated as all or nothing choices. Lower sensitivity uses can often be adopted more readily, where basic controls are in place, while higher sensitivity applications can be approached conditionally, with verification targeted where it provides the most value. We're hoping by clarifying both the technical suitability conditions and the main cost drivers, particularly transport logistics, the framework will help reduce reliance on conservative assumptions, and it will support more consistent planning decisions across councils. Looking ahead, the main opportunity is to strengthen decision confidence through improved operational data and expanded case evidence. That includes building broader council data sets on transport logistics and delivered cost behavior, improving traceability of water quality verification processes, and also continuing to capture field performance outcomes where recycled water is used. Over time, these steps would allow the framework to be refined further and support more widespread and confident adoption of recycled water where it is technically appropriate. And that concludes our presentation. So thank you everyone for listening. Apologies for the slight interruption and lag in the slides, but we hope you were able to still follow okay. Yeah, we're happy to take any feedback or questions now.
Yeah, I do have a question actually. Can you hear me?
Yeah, we can.
Cool. So I'm from BC Council, and I've looked into the possibility of using recycled water. We're very regional with very long travel between the recycled water outlets. I was wondering if you got information regarding the Tweed case on their approvals that they had in place from the EPA, if it was a blanket approval to use recycled water in the construction projects, or if they had to seek approval each project.
I think we tried looking into that, but I'm not sure we were able to find information on whether I think we concluded that for each project they had to get separate approvals. Mono, would you like to step into this? Can you confirm that for us?
I think we had a discussion with the team, I think. So he just gave us the normal criteria for that, but for the one which she is talking, I really don't know about that one.
Yeah, I think from our research, we saw that they needed a separate approval for each project, and it varied, the distances, the fill points, everything varied as well. But we weren't able to confirm that, unfortunately. So